So question number 21 says the graph shows the relationship between the force acting on a compression spring and the change in length of the spring. One of these springs is placed in each corner of a horizontal square plate. The axis of each spring is in a vertical direction. These four springs support a total load of 160 Newton. What is the elastic potential energy stored in the four springs? Now, there are four springs and each support, the four combined support a total load of 160 Newton. That means that each spring experiences a force of 40 Newton. So I go to my force extension graph or force compression graph in this case. This is 40 Newton, and that tells me that for a force of 40 newtons the change in length is equal to 2.4 millimeters. So to find out the total elastic potential energy, half into force into change in length would give me the elastic potential energy of one spring. So this is half into 40 into 2.4 into 10 to the power minus 3. But since I've got 4 springs, I'll multiply this by 4 and I end up with the answer being 0.192 joules, which is option B. Moving on to question number 22. Question 22 says which row correctly identifies the properties of all electromagnetic waves? So whether they are X-rays or infrared or UV, microwave, visible, doesn't make a difference. So as far as the first property is concerned, they're all transverse wave. So that means it has to be either A or B. C and D gets eliminated. They're not longitudinal. So once again, A or B. They can travel in free space, that is right, hence the answer is A. How do we know that they can travel in free space? We get light from the sun, we get infrared radiation from the sun. All of these electromagnetic radiation travel through space, free space. Moving on to question number 23. Question 23 says, what is the approximate range of wavelength in free space for infrared radiation? So, if you talk about visible light is 400 nanometers to 700 nanometers. And when you talk about infrared radiation are right next to visible light, and they've got a higher wavelength. They've got a lower frequency. That means the answer needs to be D. 800 nanometers to 1000 micrometers. Question 24 says, the diagram shows a car traveling at a constant speed in a straight line between person P and person Q from point X to Y. The car sounds its horn continuously as it travels. The horn emits sound of constant frequency. Which statement about what person P and what person Q hears during the motion of the car is correct? So the keywords here are, number one, the car travels at a constant speed. The car travels away from P and towards Q. Now, they're talking about the Doppler effect of sound. The Doppler effect is basically an effect in which the observed frequency of sound is different from the actual frequency due to the relative motion between the observer and the source. Person P hears a sound of increasing frequency. That is statement 1. That is incorrect. Person P will hear a sound of a frequency that is lower than the actual frequency, but the frequency won't change because the speed of the car is not changing. Person Q hears a sound of decreasing frequency. Person Q, because the car is moving towards person Q, the person would hear a sound of a higher frequency, but it would not be decreasing. Say, it would not change. So it's incorrect. Option 3 states, statement 3 states, person Q always hears the sound of a higher frequency than person P. That is absolutely right. So 3 only. So for example, let's assume. So let's say the actual frequency of the sound is 100 hertz. Person Q would hear a frequency that is greater than 100 here, but a constant value of that frequency. If it's 110 hertz, he constantly hears 110 hertz. If it's 120 hertz, he constantly hears 120 hertz. On the other hand, person P hears a sound of frequency less than 100 hertz. So if it's 90 hertz, it's a constant 90 hertz unless the speed changes, which is not happening in this case. Question 25 says a progressive wave of a frequency 300 hertz is traveling with a speed of 600 meters per second. What is the phase difference between 2 points that are a distance of 0.5 meters apart? So the first thing that we need to do in this question is work out the wavelength. So V is equals to F lambda. Hence lambda is equals to V upon F. The speed of sound is 600 and the frequency is 300, which gives us the wavelength as 2 meters. Now, one wavelength which is 2 meters represents 2 points that have a phase difference of 360 degrees. So if 2 points are one wavelength apart, that simply means that they have a phase difference of 360 degrees. So what will be the phase difference for 2 points that are 0.5 meters apart? And using simple ratios gives us the answer for x is equals to 90 degrees B. Question 26 says, polarized beam of light with intensity I is incident normally on a polarizing filter. The transmitted light has an intensity I. The filter is rotated about the normal axis through an angle theta. The transmitted light has an intensity 0.75 I. What is the angle? The formula for the transmitted intensity is I is equals to, let's call this IT, is equals to II. Let's call this transmitted and incident. IT is equals to II cos squared theta. Now in our case, the transmitted intensity is 0.75 I. 0.75 I. The incident intensity is I, and that is equals to cos squared theta. So the i's cancel out and we end up with cos squared theta is equals to 0.75, square root both sides to get rid of the square, and that gives us theta is equals to cos inverse of square root of 0.75, and theta comes out to be 30 degrees. So the answer here is A. 27 says light waves are emitted from two sources. What is a necessary condition for the observable interference fringes to be produced? The waves must be polarized. So they're talking if you have two sources and the two sources meet at a point that would form interference fringes due to constructive and destructive interference. The waves being polarized is not a necessary condition. The waves not polarized, that are also not a necessary condition. The waves must be coherent. Yes, that is necessary. The waves must have equal amplitude. Having equal amplitude ensures that the dark fringes or the destructive interference would be completely dark. But if they don't have equal amplitude, you'll still see an interference fringe, interference pattern. So D is not a necessary condition. Question 28 says the diagram shows a water wave in a shallow tank. The water is diffracted through a gap in a barrier and spreads. The wavelength of the wave is much smaller than the width of the gap. The wavelength of the wave and the width of the gap are both changed by a small amount. Which combination of changes must increase the amount of spreading due to diffraction? Now, what we can see here is the fact that our wavelength is much smaller than the width of the gap. To increase the amount of spreading, you've got two options. We can either decrease the gap size, or we can increase the wavelength, or do both, so that the wavelength and the gap become almost equal or as close to each other as possible. So increase the wavelength, decrease the gap, that would do the job, and that is option C. Question 29 says light of wavelength 567 nanometers is incident normally on a diffraction grating. The grating has 400 lines per millimeters. A number of diffraction maxima are observed on the far side of the grating. What is the angle between the second order maximum and the third order maximum? So, the formula that we have for a diffraction grating, the formula is d sine theta is equals to n lambda. D sine theta is equals to n lambda, where d in this case represents the grating spacing. Now d can also be written as 1 upon n, where n represents the number of lines per meter. We are given number of lines per millimeter. We'll have to convert this into per meter. So 1 upon n sine theta is equals to n lambda, or I can say sine theta is equals to n lines per meter multiplied by lowercase n, which is the order number, multiplied by lambda. Now, to find out the angle between the second order and the third order, we need theta. Theta is equals to sine inverse of uppercase n lines per meter, lowercase n order number times lambda. So we'll have to do this twice. We'll have to do this once to find out and plug in the value as 3 over here to find out the angle of the third order. We'll have to do this one more time and plug in the value as 2 over here to find out the angle of the second order and subtract the 2. So if I were to do this for the third order, first I would say theta 3 is equals to sine inverse into n. What was n again? N was the number of lines per meter. They have given us the number of lines per meter as 400 lines per millimeter. 400 lines per millimeter means 400 multiplied by 1000. You'll have 1000 times more lines in 1 meter into n. This is the third order, multiplied by the wavelength here, multiplied by lambda. The wavelength here is 567 nano 10 to the power minus 9, and that gives you theta 3 as 42.87. Doing the same thing again, but this time around, instead of having 3 over here, I'll plug in 2, and that would give me theta 2, which is equals to 26.97, and they're asking you for the angle between the second order maximum and the third order maximum. The angle between the two would be theta 3 minus theta 2, which is equal to 15.9 degrees. So the answer therefore is equal to C. Question 30 says two cylindrical conductors X and Y are made of from the same material. The conductors have equal lengths, but Y has a smaller diameter than X. X and Y are connected in series to a cell. Which row compares the number of charge carriers per unit time passing through X and through Y? Compare the average drift speed of the charge carriers in X and in Y. Now, these two cylinders, X and Y, that are made from the same material, they have equal lengths, but they've got different diameters. That means that they'll have different resistance, they'll have different cross-sectional area. But irrespective of what their length is, what their diameter is, or what their material is, because the two are connected in series, I know for a fact that the current would be same in X and Y. And since the current is same, that means the total charge, what is current? Charge flowing per unit time. The charge flowing per unit time would be same. And hence the number of charge carriers would be same. So Y same as X, number of charge carriers per unit time. So it's either B or D. Now let's talk about the average drift speed of charge carriers. The formula here is I is equals to N, number of charge carriers per unit volume into cross section area into the speed velocity multiplied by E, the charge of an electron. Current is constant. They're made of the same material, so number density of charge carriers is constant. They've got the same charge, so E is constant. That means A is inversely proportional to V, or V is inversely proportional to A. So the one having a greater area would have a lower drift speed, and vice versa. So from the question, I know Y has a smaller diameter. So that means Y will have a smaller area and Y will have a greater drift speed than X. The answer therefore is T. A copper wire is 6.4 meters long and has a resistance of 0.92 ohms. The resistivity of copper is 1.8 into 10 to the power minus 8 ohm meter. What is the diameter of the wire? So they've given you the resistance, they've given you the length, they've given you the resistivity, they're asking you for the diameter. The formula is R, the resistance is equals to rho L upon A. I can say area is equals to pi d squared upon 4. Or you can use pi r squared, find out the radius, double that radius and get the diameter. Area is equals to rho L upon R. The resistivity is 1.8 into 10 raised to the power minus 8. The length is 6.4 and the resistance is 0.92, and hence the area comes out to be 1.3 into 10 raised to the power minus 7 minus 10 raised to the power minus 7 meter squared. Now to work out the diameter, I know diameter is square root of area times 4 upon pi. Plug in the value for the area in the equation on the right, and that gives you the diameter as 3.992 into 10 to the power minus 4. Obviously you'll round that value up, and that gives you the answer as C. Question 32. A thermistor is connected to a cell with negligible internal resistance. Which graph shows the variation with temperature of power dissipated in the thermistor? Now, you've got multiple equations for power. You've got power is equals to VI, power is equals to I squared R, and power is equals to V squared R. So since we're changing the temperature of the thermistor, we know that a change in temperature would cause a change in resistance. Temperature, when the temperature increases, the resistance of a thermistor decreases. And that would obviously change the current. But what doesn't change is the potential difference. The thermistor gets the same potential difference as the EMF of the cell. So the equation to use here would be power is equals to V squared upon R. Now, as we increase the temperature, the resistance decreases. As the resistance decreases, the power increases. Why? Because V here is a constant. So I can conclude that an increase in temperature causes the resistance to decrease and hence the power to increase. So an increase in temperature causes the power to increase. The only option that shows this relationship, temperature increasing and the power increasing, is option A. Question number 33 says a metal electrical conductor has a resistance of 5.6 kilo ohms. A potential difference of 9 volts is applied across its ends. How many electrons pass a point in the conductor in 1 minute? Now, this requires some working. So let's. Step 1. I is equals to V upon R. Let's find out the current. The potential difference is 9 volts. The resistance is 5.6 into 10 to the power 3, 5.6 kilo ohms. That gives us the current as 0.01607 amperes. Number 1. So that is the current. Now, this is basically the number of electrons passing, the total charge in coulombs passing in 1 second. And the question is asking you for the number of electrons that pass in 1 minute. So let's first find out the number of electrons that pass in 1 minute, or the total charge that passes in 1 minute. So what I'll have to do is, if I were to do this directly, I would say 0.01607. That is the total charge in coulomb that passes in 1 second. Let's multiply it by 60 to get the total charge in coulomb that passes in 1 minute, and divide this by the charge of an electron, which is 1.6 into 10 to the power minus 19, and that would give you the answer as 6 into 10 to the power 17. These are the number of electrons that pass in 1 minute. 6 into 10 to the power 17. Question 34 says which circuit symbol does not represent an electrical component that is designed to emit sound waves? Now, this is something that students often neglect. If you go through your syllabus, you'll see there is a page that is dedicated to circuit symbol. A lot of students don't pay much heed to that, but that is part of the syllabus, which means you need to know each symbol and what that symbol represents by heart. So the reason this one is simple is most of us know that this here is not something related to sound, so the answer should be B. But what do the other symbol represent? If you talk about A represents an electric bell. If you talk about C represents a loudspeaker. If you talk about D represents a buzzer. So A, C and D, all three emit sound waves, but not B. The diagram shows a junction in a circuit where three wires P, Q and R meet. The current in P and Q are 1 ampere and 3 ampere respectively in the direction shown. How much charge passes a given point in wire R in a time of 5 seconds? So similar to the question that we did above. Now, if this is 1 ampere, which is entering this junction, this is 3 ampere that is leaving this junction, that automatically means that wire R should have a total current of 2 ampere entering the junction. Kirchhoff's first law, or the current law, says the total current entering is equals to the total current leaving. So we've got 3 amperes entering here and 3 amperes leaving here. Now, for this 2 ampere, they're asking you what is the total, how much charge passes a given point in a wire in a time of 5 seconds. This 2 ampere means 2 coulombs passing in 1 second. Or I can use Q is equals to IT. The current IT, the current is 2 amperes. You multiply that by 5 seconds and you get a total charge of 10 coulombs. Hence the answer is C. Question 36 says a cell of EMF E and internal resistance R are connected in series with a switch S and an external resistance R. The potential difference between P and Q is V. Which statement is correct when S is changed from open to closed? Okay, so initially the circuit is open and the potential difference here across P and Q is equal to V. Now what is this potential difference? This potential difference right now is equal to the EMF of the cell. Despite the cell having internal resistance, assuming that the voltmeter has infinite resistance, the voltmeter gives you the EMF of the cell. Why? Because there is no current flowing through the circuit. And since there is no current flowing through the circuit, there will be no potential drop across the internal resistance. What happens when you close this switch? Now, when the switch is closed, the circuit gets completed. And we've got some value of current flowing through the circuit. And when current flows through the circuit, there will be current flowing through the internal resistance. So there will be some potential lost in the battery across the internal distance. So this time around, this V, this V will be lesser than the previous value for V. V decreases, okay, V decreases because there is a potential difference across R, which is internal distance. If I were to just assume values so that you may find it simpler, if I am asked to do that, I would say okay, initially the EMF is 10 volts. When the circuit is open, the EMF is 10 volts, and the voltmeter will show you a value of 10 volts. The voltmeter shows a value of 10 volts. Now with the circuit closed, with the switch closed, circuit completed, what would happen is there'll be a potential drop across the internal resistance. Let's assume this value is 2 volts. And what that does is, this time around, after the circuit is closed, circuit is completed, the switch is closed, the voltmeter, the potential difference across P and Q would show you a value of 8 volts due to this loss here of 2 volts. Question 37 says, what is the general description of a baryon? A baryon is basically, it consists of 3 quarks that do not need to be of the same flavor. So a fact that you should remember, baryon made up of 3 quarks and they do not need to have the same flavor. So the answer is B. C and D are incorrect based on the fact that C and D says that it consists of 2 quarks. A is incorrect based on the fact that it says that all 3 quarks must be of the same flavor, which is not a requirement. Question 38 says, a stationary nucleus has a nucleon number A. So let's draw our stationary nucleus, and this has a nucleon number A. The nucleus decays by emitting a proton with a speed v to form a nucleus with speed u. The new nucleus and the proton move away from one another in opposite direction, which equation gives v in terms of a and u. So what has happened now is that you've got a proton that is emitted out. A proton will have a nucleon number of 1, and the nucleon number of our atom changes, or of our nucleus now, changes from A to A minus 1. And they travel in opposite direction. So this is V, and this would be U. Now, one thing that we know is that momentum is always conserved. So since the initial momentum is 0, the final momentum needs to be 0. And for the final momentum to be 0, the momentum of this should be equal to the momentum of the proton. Equal and opposite. They should be equal and opposite so that they cancel each other out. So what I'll do is, I'll say mass into velocity of our nucleus should be equal to mass into velocity of our proton. And rearranging this equation would give me V is equals to A minus 1 U, which is option B. Question 39 says, what is the change to the quark composition of a nucleus that takes place during a beta plus decay? So during a beta plus decay, let's form an equation. Let's say you've got a nucleus X with a nucleon number A and a proton number Z, and it decays into Y plus a beta particle. For the equation to balance out, Y should have a nucleon number of A and a proton number of Z minus 1. Now what I've noticed is that there is a decrease in the number of protons. So this was Z, this is Z minus 1. But the nucleon number has not changed, which means a neutron has increased. A proton gets converted into a neutron, which means proton which is up, up, down gets converted into up, down, down. This U gets converted to a D, let's say, and up gets converted to a down quark. So the answer is D. What is the charge in terms of elementary charge E on a charm quark? So there are 6 different quarks that we talk about: up quark, down, top, bottom, charm, and strange. So up, top, and charm all three of these quarks have a charge of plus 2 upon 3e. On the other hand, down, bottom, and strange, all three of these quarks have a charge of minus 1 upon 3e. So in this case, the answer would be D.